Unfortunately, most of the systems we encounter have nonlinear tolerance stack-ups. This creates significant complexities that root sum of squares cannot accommodate, but we do have alternatives. When we are faced with a nonlinear tolerance stack-up, our best alternative comes in the form of Monte Carlo simulation. Monte Carlo simulation calls for a random number generator to create a series of possible outcomes for each dimension within its respective mean and standard deviation. A minimum of 100 trials is recommended. Using mathematics, we arrive at a governing constraint equation for the gap of the system. It is important that the constraint equation for the gap behave normally. To that end, we should construct a histogram of the gap result, specifically looking for symmetry and a bell-shaped behavior. Let's consider this nonlinear example. We have a wheel of radius r moving at an angle A. A bar of length L is pinned to the wheel. The right end of the bar is constrained to move horizontally. The distance between the center of the wheel and the slot is set at distance h. The mean and standard deviation for each dimension is shown here. The gap equation is found through trigonometric manipulation. As you can see, it is highly nonlinear. We run the Monte Carlo simulation with 100 trials. The histogram of the gap shows a somewhat symmetrical, bell-shaped behavior, which we will assume to be approximately normal. Be aware that many nonlinear calculations yield non-normal distributions. There is no substitute for an investigation into the histogram and the distributive behavior of our simulated data. Here is a portion of our Monte Carlo simulation run in Excel. RG represents a random number between 0 and 1. There is a dedicated random column of values for each dimension in our tolerance stack-up. We convert these random values to the appropriate dimensions using the inverse normal and the respective mean and standard deviation from the table presented earlier. Each row represents a random output of dimensions for the system. We use the gap equation to calculate the values in the gap column for each respective value of A, R, H, and L per row. A summary is provided to the right that offers the average, standard deviation, minimum, and maximum for the gap. An upper and lower specification limit is set by the designer. We can then standardize the upper and lower specification limits using the z-score formula and calculate the corresponding probability of being below the lower spec limit and above the upper spec limit. These probabilities are areas in the tails of the normal distribution bounded by the lower and upper specification limits respectively. Here we see a 3.7% likelihood of falling below the lower spec limit and a 4.1% chance of falling above the upper spec limit.